Hey friends, on a recent episode, we talked about quantum programming with Q Sharp, the QDK, and Azure Quantum. But did you know that you can also use optimization algorithms inspired by decades of quantum physics research to help solve optimization problems? Delbert Murphy is here to show me how to use quantum inspired optimization using Azure Quantum today on Azure Friday. Hey friends, I'm Scott Hanselman and it's Azure Friday. Today I'm chatting with Delbert Murphy about Azure Quantum Optimization. How are you?
Terrific, Scott. How about yourself?
I am very well, and I'm learning all about new things that I can do to solve the problems that I have. How do I know if the problem I have needs something that is either quantum or quantum inspired to
Right.
optimize it?
And so with quantum inspired optimization, there are a whole raft of different things that you can solve with this technology.
Mhm.
And the key is just how do I find the best value, the lowest cost among an exponential number of alternatives.
Mm.
So supposing I had trouble with my shower and I needed to evaluate these different contractors and different supply houses for tile and different plumbers and different electricians and all of those sorts of things. All those different combinations and all those different variables could be part of an optimization problem. And then you want to find the best quality job at the lowest price. And so,
That is very funny because you know darn well that I have a contractor on the other side of that door right now who was selected from one. And the way I solved that problem was in Excel, and I brute forced it. And I hope I made the right decision. You know what I mean? I did the best that I could, but that may not be the global minima in that case.
right, exactly. And even more importantly, for complex supply chains or for complex distribution networks, or if you're delivering packages, or even if you're trying to optimize a portfolio. So we have a number of folks working with a number of folks in financial services where you take all these different financial instruments and you kind of make sure you have a good balance of risk, but what's going to give me the highest return in a year's time? So that's another thing you can set up in a quantum inspired optimization problem,
Mhm.
and then submit to one of our solvers. And so the probably the key element is as a developer, what we're worrying about is getting this particular problem into the format that the solver understands.
Mhm.
Then we can send it to the solver and it'll figure it out and then give us an answer back. And then we interpret that answer into this is the plumber you should use,
Mhm.
or this is the route from here to here that you should follow with your truck, or
Okay.
whatever the thing is we're trying to optimize.
So I could imagine a plumber solver that took as an input an Excel spreadsheet that was laid out a certain way. And I would read the documentation and it would say, okay, make sure that column B has this and column C has that. I wouldn't necessarily submit code. I would submit this declaration in the format that they wanted. And it's arbitrary because it would decide that B is this and C is that. Are we submitting code into the solver, or are we submitting the declaration of the
Mhm.
problem in some different format?
That's a perfect question, because we're using in this case right now in the public preview, we're using Python, and we're building up Python objects. So we're going to compose our problem in terms, and then we're going to put them in a problem, and then we're going to submit them to the solver. And the solver behind the scenes serializes it into JSON and so on and so forth. But the basic idea is we're using Python artifacts to represent this problem. And the kind of the linchpin concept here is that for these solvers, we have 6 of them right now in Azure Quantum. These solvers are based on binary variables, or binary decision variables, we call them. So
Okay.
those variables can be either be 0 or 1, or they can be 1 and -1.
Interesting. Okay. So if I want to do these kind of things and learn about the kind of things, am I buying a quantum machine? Am I renting quantum time? But these are inspired by quantum algorithms, but they are not necessarily using the real machine, right?
Correct. They're inspired by quantum and they run on just regular CPUs, GPUs, or FPGAs in Azure. And so it's just a matter of setting up your Azure Quantum workspace and then connecting to that with a Python client and then sending your requests to the solver.
Okay, let's see if we can try to make this as concrete as possible. And maybe you can give me a demo and we can really nail this down, because I think a lot of people are stretched just about where their limitation of understanding is right now.
Yeah, no, we are kind of in the clouds right at the moment. So why don't we do the classic Secret Santa or white elephant gift kind of example? The Secret Santa is one where you get a group of folks together and they all decide, okay, we're going to buy a nominal gift. And in this case, write a poem for the person whose name we draw from the raffle. Okay. So here's my analog computer here. And I have 3 people who are going to participate in this raffle. So Tess, Uma, and Vincent. So
Okay.
T, U, and V. And if you remember from Kerberos, we had Alice and Bob, A and B. That's last millennium. No more. Modern is T, U, and V, Tess, Uma, and Vincent. So what I do is I mix this up, right? And then let's pretend I'm Vincent for a second. I reach into the jar, right, without looking, and I pull out a name. And that's the person I'm going to buy a small gift for and write them a poem. Mm-hmm. Scott Hanselman.
We need an S, T,
yeah,
U, G, so.
just to really get it. Yeah, and it's in the string of variables. So in this case, it's Uma. So Vincent is going to buy Uma a gift and write her a poem. Now, quick question, Scott. Do I put the slip of paper back in the jar?
Well, it depends on the problem that you're trying to solve. But in this case here, Uma gets a gift, so I think she's good for the holiday.
Right. And so then Tess and Uma are going to draw out of here next, right? And so it's just whatever. It's just these 2 that are left, because this one should only be used. Each one should only be used once. Right. Which is a really important part of how we solve this particular problem. Okay. So then if I'm Uma, I might pull out and I'll get Tess. Okay. And then if I'm Tess, I'll pull out and I'll get Vincent.
Everybody wins.
So each person buys another person a gift, and each person receives just one gift. Okay.
Sounds perfect. Sounds like a self-optimizing problem.
That's right. Well, it's easy with Tess, Uma, and Vincent. But let's pretend for a second, what if I wanted to do this with all of your Twitter followers?
Well, yeah, then it would start getting...
It'd get pretty crazy, right? I can't fit 262,000 names in slips of paper in the jar. So yeah, we'd have to do something more scalable, and Azure Quantum to the rescue. The QIO service would scale to that many variables. And so it's not an issue. So we can take a look at the code perhaps and kind of jump in there and see how we actually code this solution up. So if we look here at our matrix, right? This is this little matrix just kind of helps me represent the problem. So,
so this is a Python comment block here. You've drawn yourself a little ASCII table.
Perfect. Yeah. Thank you. Yeah. So this is a little Python script, and I just run it in my case, Anaconda Python, and there's a QIO package. So it's in PyPy. You just pip install it and you're off and running. Okay. So yeah, so it is a very simple setup. So and remember again, now we've got these variables that are either 0, go over here, or 1. Okay. So If Vincent is going to buy Tess a gift, that is our first variable is going to be 1 in that case. Okay. If Vincent is going to buy Uma a gift, then that variable is going to be a 1 in this case. And then you can see the same would be for Tess buying Vincent a gift or Tess buying Uma a gift, and then Uma buying other folks a gift. And then the nice thing about these binary variables is if you leave the option out, the solver's not going to pick it. Okay. So we don't have a variable for Vincent buying Vincent a gift or Tess buying Tess a gift or Uma buying Uma a gift. And that way we don't have that problem where sometimes with the Secret Santa, you reach in and you draw your own name out of the hat, right? Mm-hmm. And then you've got to say, oh, that's me. I got to put it back and draw another one.
But right? You made the comment that if we did this for hundreds of thousands of people, how does line 80 and your table not get that large? How do you iterate? How do you take that and do it n times? Right now you're doing it statically 3 times.
Right. So you would just put that in a larger loop that could either read a database table with the 260 all the Twitter followers in it, mm-hmm. or you have some way of getting those things. And again, that's part of the job of the developer here. When you might be reading data from existing systems and putting them into this problem and then sending it to the solver and getting it back. And then you can send that data back to the originating system if you want.
Okay, cool.
So these columns all have to be, these column values need to be mutually exclusive, and the row values need to be mutually exclusive. So if we think about that for a second, mm-hmm. they can be either 0 or 1, right? What you can do is you can apply this formula here, right here. Oop.
Okay.
Got to make a slight.
I do my quantum computing. I do it in production like you do. So.
Well, no, this was a comment, so it doesn't affect my run, obviously.
I'm just playing.
So the idea is, if I've got the variable and I want one of them to be 0 and I want one of them to be 1. Okay. So if I add 0 and 0 and subtract 1 and then square it, I'm going to get the value 1, which is a higher, it would raise my cost function. But if one of the variables is 0 and one of the variables is 1, then the 0 plus 1 is 1. Mm-hmm. Minus 1 would give me 0. And then I square that and I still have 0. So I'm trying to minimize my cost function. So I'm going to end up with a cost function of 0 if I have the rest of the constraints set up properly, right? Mm-hmm. So if only one person is given one gift and one person buys a gift for one other person, okay? We have to take this little formula here,
right,
and expand it. So this is the algebra that you have to do. If you've tutored someone or helped someone with their algebra homework, perhaps a child or a grandchild, then this is pretty straightforward.
Well, so just to make sure that we're clear, though, so we don't make any assumptions, the 2 asterisks are indicating an exponent?
Right, squaring.
Okay, you're squaring, not using a little hat, not using shift correct. 6. Okay, yeah. So that represents, the function x and the passes in I, and then you're squaring that. So you're taking 3 terms and then squaring it all out, like doing FOIL, except you're doing it on 3 things, and you're getting all the way out. So line 31 expands into line 33.
Right. And line 33 then is I would take my first variable and square it. Mm-hmm. Then I take my second and add it to my second variable and square it. And then take a coefficient of 2 and 1 of each variable, and a coefficient of -2 and 1 of each one of one variable there, and then -2 in the other variable, and +1.
And then you're taking the function, the now expanded expression on line 33, and you've now broken it down, and each of those 6 then gets loaded into the terms array.
Right.
Gotcha.
And then I'm adding these terms together because I need to do the 6 combinations.
Gotcha.
So this is the little subroutine here. So it's called build terms in 2 of the variables. I'll learn this yet. Okay. So then what happens here is here's row 0, right? These 2 terms. And then row 1 are these 2 terms, and row 2 are these 2, and then here are the columns.
Right. So build terms is your helper function that's making the expression, the if I may, the document object model of the math problem, and then you're making n number of them. In this case, where n is 5.
Right. And so, or 6, I think.
I see 6 there. Sorry, my apologies. Yes, it is 6.
Yes. Okay. So then what we do in Python is we just create this object called a problem, and we tell it, okay, I want to use the simulated annealing solver, and we got this really slick help here too, so you know exactly what goes in there. The other thing about these solvers is there's a parameter-free version. So word to the wise, always start with the parameter-free version. Let the solver look at your problem and figure out, well, what parameters should I set up? Okay. And so in this case, I'm just going to then print out the solver. I'm going to call the solver, and I'm going to get the result back. So let's do that real quick here.
While you're doing that, annealing is a thing that's used in metallurgy. When you heat something up and then cool it down, and simulated annealing, the math people took that word annealing and brought it into the math world and gave it a different meaning.
Yeah, and it actually, too, for quantum physics, it's even about exciting a system of particles, getting them bouncing all around.
Right, because that's what happens when you heat things up.
Cooling, right, and then cooling things down. So then as they cool down, they settle, and we want them to settle in that lowest cost. So that's exactly, and so you're exactly right. The quantum inspired here really is inspired by quantum physics. It's just like there's another solver called substochastic Monte Carlo, and it's actually built on the adiabatic theorem from quantum physics. So there really is quantum stuff in here. And so here again, I am in Anaconda Python, and I've got an environment called QIO that I run my quantum inspired optimization in, and so I'm just going to run that Python code there in Secret Santa. So here we go. There we go. And so this here are the terms. So this was the explosion of the terms. And then here I call the solver, and here's the answer I get back. So what I need to do as a developer is turn that kind of a little bit of a gobbledygook answer into the right result. In this case, Vincent's going to buy Tess a gift and write her a poem. Tess is going to buy Uma a gift and write her a poem, and then Uma is going to buy Vincent a gift and write him a poem. Okay, so those are the kind of the jobs of the developer in this case are to cast the problem, cast the business problem into this problem we can send to the solver. The solver is going to do all the hard work of finding the best option. And then we have to take that option that we get back that it picked and translate that for our folks, in this case, Vincent, Tess, and Uma, so that everybody knows, who needs to buy whom a gift.
So a couple of ignorant questions to make sure that we understand. So this is sending the problem somewhere, or the problem is happening locally? The work is not happening here. It has been sent off into the cloud?
Correct. So we actually send that into the Azure Quantum workspace. And
And it's
yeah,
solved by traditional machines, not by a quantum machine. It's just quantum inspired. So I didn't burn up my credit card by spending quantum money.
correct.
Okay.
Correct. This is
And
just
on Azure, I get like minutes. Like I get like, on Azure DevOps, I have 1,800 minutes of build and I have this many minutes on my website. Can I sign up for this now, or is this going to cost me a lot of money?
absolutely no. That's the beauty of this is that there's a developer SKU that gives you a free hour every month of development time. And if you look, I'd have to pull it. I'll have to pull it up.
Well, I noticed that it said cost right there, 0. Whatever it
That's
was you did was not a hard problem, so it cost very little, probably a couple of decimal points to the right there.
actually that's probably true in this case, but that cost, this particular cost here, is the value of the cost function at the end.
My apologies.
So, right.
We have about an hour. This didn't feel like it took very long, so presumably I could do this dozens or hundreds of times and not even get close to using up my developer credits.
Correct. That's absolutely correct. And it's really just a matter of the time that you want to invest. And so this is a great way to get started with this, to learn. And go ahead, folks can ping us on the Microsoft Q&A. Mm-hmm. There's a hashtag Azure Quantum and on Stack Overflow Azure Quantum. So you can give these things a try. This code's also on GitHub, so you can get a copy. And then we also have some other samples about loading containers on ships and a little bit of the classic traveling salesperson on the Azure Quantum GitHub site. And so folks can start with those. And then one other really quick note is that there are a couple of research papers that we'll tag, but these are actually recipes for how to come up with solutions to some of these problems. So this is Andrew Lucas. And if you look here, these classic problems you may remember from school, right? Exact cover, set packing, satisfiability, knapsack problem, graph coloring, traveling salesperson, and so on. So here they give you the formulas that you can kind of plug into your code. And so the other thing that's really important is that we're taking these formulas and building them into code, and then we'll be posting those on GitHub as part of the developer support that, or the kind of getting started support that we're putting out there.
Okay, so let me see if I understand, right? If I look at patterns in kind of classical computing and I say, oh yeah, that looks like time for a bubble sort, then I know what to go and Google with Bing for to go and learn about that. And in this world, those algorithms have names. We know if like traveling salesman is one we may have all learned in school. Some of these may not be familiar, particularly like around people who don't have a math background, like the Hamiltonian ones. But as you learn these different names and patterns, you go, hey, factory pattern, hey, bubble sort, hey, stochastic Monte Carlo, then you know that that's going to be supported by the QIO libraries.
Exactly. And so you'll actually get to the point where if you're trying to like figure out packages on vehicles and how to send the vehicles around to do the delivery, that's actually a combination of traveling salesperson plus knapsack. So you put those two together, and you could literally add the cost functions together. You just have to make sure that sometimes you have to balance the two against each other. So the traveling salesperson part doesn't override the knapsack part, and vice versa. And so there's some ways you can tweak that. But yeah, that's really it. The Lucas paper is kind of one of the things that everybody talks about when they're working on these things.
Cool. So we're going to make sure we have links in the show notes for all of this stuff. But what's your number one place to go to learn more?
The number one place is our documentation, our documentation site here. So it's the docs.microsoft.com.
Okay. So once you're into Azure Quantum, if you start at what are quantum-inspired algorithms, that will let you go off into key concepts, how to optimize, how to think about this stuff, and then lead us into your GitHubs and your sample problems.
Yes, exactly.
Very cool. Well, thanks so much for chatting with me today.
Thanks a lot, Scott, for having me. This is tremendous.
All right. I have been learning from Delbert Murphy all about quantum-inspired optimization today on Azure Friday. Hey, thanks for watching this episode of Azure Friday. Now I need you to like it, comment on it, tell your friends, retweet it. Watch more Azure Friday.